Across the entire observable universe, spanning 13.8 billion years of cosmic evolution and encompassing hundreds of billions of galaxies each containing hundreds of billions of stars, matter dominates the inventory of baryonic substance with such overwhelming prevalence that antimatter, its perfect mirror image counterpart, predicted by Paul Dirac's relativistic quantum equations in 1928 and confirmed experimentally through Carl Anderson's cloud chamber observations of positrons in 1932, exists only in trace quantities produced by high-energy processes in cosmic ray collisions, radioactive decay, and the immediate vicinity of black hole accretion disks, each antiparticle carrying opposite electric charge to its matter, equivalent while possessing identical mass and spin, destined for instantaneous mutual annihilation upon contact with ordinary matter in reactions that convert 100% of the combined rest mass into pure energy following Einstein's equation with perfect efficiency unmatched by any chemical combustion or nuclear process. Within the framework of particle physics, a single gram of antimatter brought into contact with a gram of ordinary matter would release energy equivalent to the detonation of approximately 43 kilotons of TNT, exceeding the yield of the atomic bomb deployed over Nagasaki and surpassing by factors of millions the energy density achievable through chemical explosives or conventional propellants. This extraordinary energy release occurring not through the rearrangement of atomic bonds or the conversion of small fractions of mass to energy via nuclear binding forces, but rather through the complete transformation of matter and antimatter into gamma-ray photons carrying the entirety of the annihilated mass as electromagnetic radiation propagating at light speed from the interaction point. The question implicit in recognizing antimatter's existence and its properties, in understanding both its theoretical prediction through relativistic quantum mechanics and its empirical confirmation through particle physics experiments, concerns not merely the technical challenges of producing, containing, and controlling this most energy-dense substance known to physics, but rather the profound mystery of why the universe contains matter at all, rather than existing as a sea of photons left over from symmetric matter, antimatter annihilation, in the earliest moments after the Big Bang, and furthermore what consequences would follow from mastering the production and manipulation of antimatter at scales sufficient to enable practical applications in energy generation, propulsion systems, or weaponry that would harness the ultimate efficiency of mass-energy conversion. The theoretical foundation underlying antimatter's existence emerges from the marriage of quantum mechanics and special relativity accomplished through Dirac's relativistic wave equation, which describes the quantum behavior of spin 1/2 particles such as electrons while incorporating the requirements of special relativity. The mathematical structure of this equation naturally producing both positive and negative energy solutions that initially puzzled Dirac until he recognized that the negative energy states could be reinterpreted as describing antiparticles, particles with opposite charge but otherwise identical properties to their matter, counterparts, moving forward in time but appearing mathematically as ordinary particles moving backward through time's dimension. The symmetry between matter and antimatter extends beyond simple charge conjugation to encompass a deeper principle known as CPT symmetry, which states that the laws of physics remain unchanged under the combined operations of charge conjugation, transforming particles to antiparticles, parity inversion reflecting spatial coordinates through the origin, and time reversal changing the direction of temporal evolution. This fundamental symmetry representing one of the most robust principles in theoretical physics, and suggesting that antimatter should behave precisely as matter would in a mirror universe where left and right are reversed, charges are flipped, and time runs backward. The experimental verification of antimatter's properties has proceeded through decades of increasingly sophisticated particle physics experiments, from Anderson's initial positron discovery in cosmic ray tracks through the production of antiprotons at Berkeley's Bevatron accelerator in 1955, the creation of antihydrogen atoms at CERN in 1995 combining antiprotons and positrons into electrically neutral antimatter atoms, and eventually the magnetic trapping and spectroscopic study of antihydrogen to verify that antimatter atoms absorb and emit light at precisely the same wavelengths as their matter equivalents, confirming the predicted perfect symmetry between matter and antimatter properties, down to parts per billion measurement precision. The production of antimatter in terrestrial laboratories requires enormous energy input to create particle-antiparticle pairs from pure energy in accordance with Einstein's mass-energy equivalence, the minimum energy threshold for pair production being twice the rest mass energy of the particles being created, for electron-positron pairs requiring approximately 1 million electron volts, and for proton-antiproton pairs demanding nearly 2 billion electron volts. These energies supplied by particle accelerators that slam ordinary particles into fixed targets or collide counter-propagating particle beams to concentrate sufficient energy density in small volumes of space for brief instants. The efficiency of antimatter production through current accelerator technologies remains extraordinarily low, as the vast majority of collision energy dissipates through the production of many other particle species and the acceleration of debris, particles to high velocities, only tiny fractions of the input energy ultimately appearing in the rest mass of captured antiparticles. Current estimates suggesting that producing a single gram of antiprotons using CERN's facilities would require approximately 100 trillion kilowatt-hours of energy at costs exceeding $60 trillion, rendering large-scale antimatter production economically prohibitive with present technology and establishing antimatter as literally the most expensive substance ever created by humanity, measured in cost per unit mass. The containment of antimatter once produced presents challenges as formidable as its creation, since any contact between antimatter and ordinary matter results in immediate annihilation, conventional containers fabricated from atoms proving useless for storing antiparticles that would annihilate upon touching container walls, the solution requiring electromagnetic confinement in ultra-high vacuum chambers, where charged antiparticles remain suspended in carefully configured magnetic or electric fields that prevent contact with material surfaces. These penning traps or Paul traps using combinations of static and oscillating fields to confine antiparticles in small volumes for periods extending from minutes to months, depending on vacuum quality and field stability. Though even the best vacuum chambers contain residual gas molecules at densities of millions per cubic centimeter, each collision between antimatter and residual gas causing annihilation events that gradually deplete stored antimatter populations. Within the annihilation process itself, when matter and antimatter particles meet, their interaction proceeds through quantum field theory processes that convert the particle-antiparticle pair into bosons, force-carrying particles that mediate interactions between matter fields. The specific annihilation products depending on the initial particle types and their collision energy, electron-positron annihilation, typically producing 2 or 3 gamma-ray photons with energies summing to the combined rest mass energy of 1.02 million electron volts, while proton-antiproton annihilation generates complex cascades of pions, kaons, and other mesons that subsequently decay into muons, electrons, positrons, neutrinos, and ultimately gamma rays and neutrinos as the only stable products, the entire process unfolding in timescales of approximately 10 to the minus 23rd seconds from initial contact to final stable particle production. The energy spectrum of annihilation products spans from high-energy gamma rays, carrying hundreds of millions of electron volts, down to neutrinos that escape detection, carrying away significant fractions of the annihilation energy, as particles that interact only through weak nuclear force and gravity. Passing through ordinary matter with such low interaction probability that they traverse the entire Earth with negligible absorption, this neutrino. Energy representing loss channels that reduce the practical efficiency of antimatter annihilation as an energy source below the theoretical 100% conversion of mass to usable energy. The radiation produced by matter-antimatter annihilation poses severe hazards to biological tissue and electronic systems, as high-energy gamma rays deposit their energy through Compton scattering and pair production processes that ionize atoms and break molecular bonds throughout irradiated materials, delivering lethal radiation doses at distances of hundreds of meters from even gram-scale annihilation events, requiring massive shielding to protect nearby structures and organisms from the penetrating radiation that passes through meters of concrete or lead, before sufficient attenuation occurs to reduce intensities to survivable levels. The cosmic abundance of antimatter, or rather its striking scarcity compared to matter, represents one of the profound mysteries in cosmology and particle physics, as the standard model of particle physics predicts that the Big Bang should have produced equal quantities of matter and antimatter, every quark matched by an antiquark and every lepton by an antilepton, the subsequent cosmic evolution then resulting in nearly complete mutual annihilation that should have left the universe filled with gamma-ray photons with only tiny residual populations of matter or antimatter surviving as statistical fluctuations in the annihilation process. Yet observations reveal a universe composed almost entirely of matter, with antimatter appearing only as transient production in high-energy events. The resolution to this asymmetry problem requires physics beyond the standard model, mechanisms that violate baryon number conservation, or generate slight asymmetries in the decay rates of exotic particles in the early universe when temperatures exceeded trillions of degrees Kelvin and particle-antiparticle pairs formed and annihilated in thermal equilibrium. These asymmetry mechanisms producing perhaps one extra matter particle for every 10 billion matter-antimatter pairs. This tiny excess surviving when temperatures dropped below thresholds for pair production, and the remaining matter-antimatter pairs annihilated, leaving the observed matter-dominated universe enriched by factors of billions, compared to the antimatter abundance that would result from symmetric production, without asymmetry generating processes. The search for primordial antimatter in the present universe continues through multiple experimental approaches: cosmic ray detectors seeking anti-helium nuclei that would signal the existence of antimatter-dominated regions of space, gamma-ray telescopes searching for the distinctive signatures of matter, antimatter annihilation, at boundaries between hypothetical matter and antimatter domains, and precision studies of the cosmic microwave background radiation seeking evidence of enhanced photon production from large-scale annihilation in the early universe, all searches consistently returning null results that constrain any surviving antimatter domains to existing beyond the observable universe or being suppressed to undetectable levels by the matter-antimatter asymmetry mechanisms operating in the first microseconds after the Big Bang. Surrounding the fundamental physics and cosmic questions about antimatter, practical applications remain largely theoretical due to the enormous challenges of production, storage, and controlled annihilation. Yet certain niche applications in medicine have already been realized through positron emission tomography, a medical imaging technique that injects radioactive isotopes producing positrons through beta plus decay into patients, these positrons traveling short distances through tissue before encountering electrons and annihilating to produce back-to-back gamma-ray photons detected by surrounding sensors, the coincident detection of paired photons enabling precise localization of the radioactive tracer and generating three-dimensional images of metabolic activity with resolution approaching millimeters. This technique now routine in cancer diagnosis, neurological assessment and cardiac evaluation, despite utilizing antimatter produced through radioactive decay rather than accelerator generation. The propulsion applications of antimatter remain aspirational concepts explored primarily through theoretical studies and preliminary engineering analyses as the extraordinary energy density of matter. Antimatter annihilation would enable spacecraft to achieve velocities approaching significant fractions of light speed if sufficient antimatter could be produced, stored, and safely annihilated in controlled propulsion systems. Preliminary designs suggesting that a spacecraft carrying milligrams or grams of antimatter could accelerate to velocities of thousands of kilometers per second through magnetic nozzle systems that channel charged annihilation products to generate thrust, potentially enabling missions to nearby stars within human lifetimes, rather than the millennia required for chemical or even nuclear propulsion systems. The weapons applications of antimatter, while theoretically feasible given its unprecedented energy density, remain impractical at present due to production costs and containment challenges that far exceed the expenses and complexities of nuclear weapons, though theoretical studies indicate that antimatter bombs containing grams or kilograms of antimatter would release explosive yields rivaling or exceeding thermonuclear weapons, while producing primarily gamma radiation, rather than the radioactive fallout characteristic of fission and fusion devices. The military implications of such weapons remaining speculative given the technological barriers preventing their development, with current or foreseeable near-term capabilities. Beyond the technological applications and challenges, the study of antimatter has revealed fundamental insights into the structure of physical law and the nature of symmetry in physics, as the precise equivalence between matter and antimatter properties constrains possible extensions to the standard model and provides stringent tests of CPT symmetry that represent cornerstones of quantum field theory. Any observed violation of matter-antimatter symmetry, beyond the weak CP violation already discovered in kaon, and B-meson systems would indicate physics beyond current theoretical frameworks and potentially point toward explanations for the cosmic matter, antimatter asymmetry, or connections to quantum gravity theories that predict tiny symmetry violations at energies approaching the Planck scale. The magnetic moment of the antiproton has been measured to agree with the proton's magnetic moment to better than parts per billion precision through experiments at CERN's antiproton decelerator facility, where antiprotons cooled to temperatures within degrees of absolute zero remain trapped in magnetic bottles for months at a time, enabling spectroscopic measurements and comparisons with theoretical predictions that verify quantum electrodynamics calculations to unprecedented precision. These measurements representing the most stringent tests of CPT symmetry for baryons and constraining hypothetical antimatter-specific forces or interactions to levels many orders of magnitude below detectable thresholds. The gravitational behavior of antimatter remains experimentally unverified, despite theoretical predictions from general relativity that antimatter should fall downward in Earth's gravitational field with precisely the same acceleration as ordinary matter. Proposals for direct measurement of antihydrogen, gravitational acceleration through ultra-cold atom, interferometry or precision trajectory measurements promise to test this prediction within the coming decades, confirming general relativity's treatment of antimatter as equivalent to matter for gravitational interactions, or potentially revealing violations that would revolutionize understanding of gravity and its relationship to other fundamental forces. The production facilities for antimatter have evolved from early particle accelerators designed primarily for nuclear physics research into specialized antimatter factories optimized for antiproton production and storage, CERN's antiproton decelerator representing the world's primary antimatter research facility, where antiprotons produced by colliding high-energy protons with metal targets undergo systematic cooling through stochastic and electron cooling techniques that reduce their kinetic energies by factors of billions, transforming high-velocity antiprotons emerging from production targets into ultra-cold antiprotons moving slower than typical molecules in room-temperature gas. These cooled antiprotons then combined with positrons produced by radioactive sodium-22 sources to synthesize antihydrogen atoms that can be magnetically trapped despite their electrical neutrality through exploitation of their magnetic dipole moments that couple to magnetic field gradients. The experimental programs studying antihydrogen pursue detailed spectroscopic comparisons with ordinary hydrogen, measuring the frequencies of optical and microwave transitions between quantum states to verify that antimatter atoms absorb and emit photons at precisely the wavelength predicted by quantum mechanics with ordinary matter, recent measurements achieving precision of parts per trillion in comparing antihydrogen and hydrogen spectroscopy, confirming CPT symmetry predictions while searching for any anomalous differences that might explain the cosmic matter, antimatter asymmetry, or reveal physics beyond the standard model, each improvement in measurement precision narrowing the possible parameter space for new physics, while simultaneously demonstrating the extraordinary difficulty of detecting subtle symmetry violations against backgrounds of experimental noise and systematic effects that challenge even the most carefully controlled atomic physics measurements. The energy economics of antimatter utilization remain fundamentally constrained by thermodynamic considerations and the efficiency limitations of particle production processes, as creating antimatter through accelerator collisions necessarily dissipates vast quantities of energy as heat, radiation, and the kinetic energy of unwanted particle species that far exceed the rest mass energy ultimately stored in captured antiparticles, current production efficiencies of approximately 10 billionths, meaning that only one part in 100 billion of the input electrical energy appears as antiproton rest mass. The remaining energy deposited into accelerator components, cooling systems, and particle absorbers. This extreme inefficiency arising from fundamental physics rather than engineering limitations as the cross-sections for antiproton production remains small compared to other reaction channels that dominate particle collision outcomes. Future antimatter production systems might improve efficiency through targeted approaches such as enhanced pair production, using ultra-intense laser fields, focused to energy densities approaching the Schwinger limit, where vacuum itself becomes unstable to spontaneous particle-antiparticle pair creation, though even optimistic projections suggest efficiency improvements of perhaps 3 or 4 orders of magnitude, rather than the 8 or 9 orders of magnitude required to make antimatter production energetically favorable compared to conventional energy storage in chemical bonds or nuclear isotopes. The fundamental challenge being that antimatter represents stored energy rather than an energy source, each antiparticle requiring more energy to create than it releases upon annihilation when production inefficiencies are included, making antimatter useful only as an energy storage medium rather than a net energy generator, unless natural antimatter accumulations could be harvested from cosmic sources where production occurs through astrophysical processes unavailable in terrestrial laboratories. Across all considerations of antimatter's properties, production challenges, containment requirements, annihilation characteristics, cosmic abundance, and potential applications, the fundamental nature of antimatter as matter's perfect opposite emerges as both a confirmation of theoretical physics predictions and a source of ongoing mysteries about the universe's composition and evolution, as the Standard Model successfully predicts antimatter's existence and properties with extraordinary precision while simultaneously failing to explain why matter dominates the observable universe by such overwhelming margins. This asymmetry, representing perhaps the most significant unsolved problem at the intersection of particle physics and cosmology, suggesting that the physics governing the earliest moments of cosmic evolution involved processes beyond current theoretical understanding, potentially connected to grand unified theories that merge electromagnetic, weak, and strong forces at extremely high energies, or to quantum gravity effects operating at the Planck scale, where space-time itself becomes quantum mechanical, and classical notions of particles and fields break down into a more fundamental description not yet captured by present theories. The study of antimatter continues through experimental programs at CERN, Fermilab, and other facilities worldwide, each measurement of antimatter properties refining constraints on possible new physics, each improvement in production and trapping technology expanding the parameter space accessible to precision measurements, and each theoretical advance in understanding baryogenesis mechanisms suggesting new experimental signatures to search for in particle collisions, cosmic ray observations, or cosmological data, the entire enterprise exemplifying how the most fundamental questions about nature's building blocks and the universe's origin remain intertwined with practical challenges of engineering the most difficult to produce and dangerous to handle substance in physics, antimatter representing simultaneously the ultimate expression of mass-energy conversion efficiency and an enduring reminder that the universe contains deep mysteries about why matter exists at all, rather than having annihilated completely with antimatter in the moments following the Big Bang, leaving only photons expanding through an empty cosmos devoid of atoms, stars, planets, or the structures that enable the existence of observers capable of contemplating their own origins, and the curious asymmetry that permitted matter to persist where symmetry would have predicted only light.